Hi everyone, welcome to this channel. So in this video we are discussing on the second portfolio idea, which is time series analysis or rather time series forecasting. If you have already watched my first video, which is the portfolio idea 1 with churn analysis, and this is the second one. Why did I decide on time series analysis is because in every organization this is one of the main important analysis done in every team to understand how the organization work or how based on the pattern. So let's get started. When it comes to definition, time series analysis is a specific way of analyzing a sequence of data points collected over an interval of time. In time series, an analyst record data or collect data at a consistent time, and now let's get into understanding why organization use time series analysis or time series forecasting to understand the business. So the first point is that it helps the organization to understand the underlying cause of trends and systematic patterns over the time. So this is the first main cause why organization would like to pursue or try to do a time series analysis. The second point is, with the help of time series analysis in terms of data visualization, business users can see seasonal trends and dig deeper into why these trends occur. So that is the second point why business users or organization would like to see would like to perform time series analysis. And the third point is, this forecast helps them to see the likelihood of future events based on the history data. So this is another important point why the organizations particularly use time series analysis. And now when come to examples, we have several examples. Some of them are sales forecasting, stock market analysis, inventory studies, which is basically demand and supply forecast, temperature forecasting. And there are many more use cases where time series forecast is useful and where the organizations or the users can make use of this analysis to understand and forecast or predict the future. So let's get started with the portfolio. It's a pollution data from 2014 to 2019, sampled every 10 minutes along with extra weather just pressure, temperature, etc. However, since this is sampled at 10 minutes, we have resampled this data set to a daily frequency, because to be honest, in a real-time scenario, 10 minutes is not something that people do time series. So that's the reason it's been resampled to 1 minute. I mean 1 day ahead. So this is all about the data set, guys. And if you come to the first cell is none other than importing the necessary libraries. So we have several libraries, such as all common libraries to be imported, such as we are calling square root for math because we are doing certain calculations while running the models. And then we have matplotlib, numpy, pandas. Stats model is something that we use for calling the time series related models, which you will be seeing later part of the video. We have also linear models called upon, which is a linear regression. The reason being, we are plotting the trend to understand how the trend goes. So that's the reason we are having the linear regression and pre-processing of standard scalar. And as you can see, we have the stats model TSA. TSA is the widely used model that for the series analysis, and we are calling upon certain algorithms that will be discussed in this video. Algorithms like ARIMA, ARMA, and exponential smoothing, simple exponential smoothing, and we also are calling upon functions like seasonal decompose and SARIMAX. And obviously we are doing the test to identify if the data series is a stationary or non-stationary. So we are calling upon AB Fuller, which will be discussed later in the video, and the parameters are called also. And if you see these two metrics, if you look into these two metrics, you'll identify that these are the values or functions that I called upon from the two other Python file. So I have another file which is called the metrics file, where I have a function called evaluate. So I'm calling using this syntax, and I have another file which is called plots, and I'm calling upon bar metrics function. Later on, we are ignoring the writing a syntax for ignoring the warnings, And we have also set up another extra settings, which is getting the random seed to be 42 and having styling upon some axis label size, X tick label size, Y tick label size, and the colors. So let's get started with the loading the dataset. So if you see this is an air pollution dataset, guys, as I already mentioned, and for a time series you always have to index your date column. So that is the second sentence. If you can see, I have indexed the date column, and if you print out the head, you can see this is the first few rows of the dataset. As usual, you can also look into the describe function, where it provides the count, mean, standard deviation, min, max, and at the same time all the interquartile ranges, it is 25%, 50%, 75%. And here let's plot each column value, guys. So if you can see, these are the column values. You can see with respect to the column names, that is pollution yesterday, rain, snow, when pressure, temperature, dew, all that. So all that, if you this is just to understand how the distribution is. So you can see the plots are giving a bit of a cyclical or a seasonal the plot on the pollution today, which is an important feature that we have. So if you see, these are the point they plots within the point, that is from 2010 to 2015. So we have as you can see, there are a lot of dips and there are a lot of spikes or peaks in the diagram. And the very first step in a time series is to decompose the time series there. So one of the most common is to decompose into multiple parts. So and the parts are nothing but we are dividing this time series into level, trend, seasonality, and noise. And all of these series contain level, noise, and but sometimes you may not see trend or you may not see seasonality. So that's why we are kind of splitting the whole plot to identify if there are any seasonality present or if there are any trend, and what can we do about it. So there are two models, which is called the level additive model and the multiplicative model. So for the additive model, this is the formula, guys. Obviously, these are models are linear. Trend is linear. Seasonality has constant frequency and amplitude, and change is constant over time. So for the multiplicative model, you can see it's all multiplicative and they are non-linear. Here the trend is curve and seasonality is not constant. Change is also not constant over time. So we need to analyze this time series by decomposing and also identify each of these different parts and see how it affects your model. So let's start by decomposing, and the very first important function used for decomposing is nothing but seasonal compose, which this function basically automatically decomposes a time series. You don't have to write a whole code on it manually. So from this function from the stats model Python library will do it for you. So after running this syntax, guys, you can see this is our data. So you can see we have the residual, which is nothing but the noise. We have the seasonal plot, we have the trend plot, we also have the observed plot. Observed is nothing but the original plot that we have as per the data set. The trend, as you can see, there are kind of curvy trends, like sometimes it's up, sometimes it's down. And seasonal, we can see there is a repetition of some seasons showing. And noise, obviously there is noise. And there is one caveat, guys. Whenever you plot seasonal decompose function, you get the plots twice. I don't understand why it is, but I'll definitely look into it and get back to you if there is any particular reason why it happens. So now there are other methods to check trend in the series. So automatic decomposing is one method that you have seen earlier, and there are other methods like finding the moving average or fitting a linear regression model to identify a trend. So like you said, seen in the libraries, import library section where I've imported the linear regression model. Automatic decompose is nothing but I'm calling the result trend that we have already got from the above section, and moving average is nothing but you are moving the mean for another 12 steps. Then we can then call upon the linear regression to identify the trend. So here you can see I've used the linear regression model and used the model to fit and then calculate the trend, and this trend is then used for identifying the trend fit by linear regression. So this is the plot, guys, and we can see that the series does not have much of a strong trend, and the results from the automatic decompose trend and the moving average looks like more of a seasonality effect, and along with the noise, and yeah, so we will also try to split our series into smaller ones to identify like if there are any other trends we can see within a weekly basis or an daily basis. Trend what we basically what will next do is to look into seasonality. So seasonality is basically observed when there is any specific repeated patterns uh, between certain regular intervals, and sometimes it could be due to seasonal factors, like for example in a sales forecasting you would find that there is a huge festival happened. For example, at Christmas there are a lot of discounts happening, and you so these are the terms with so these are the things that you need to remind yourself or keep in mind when you look for seasonality. So let's go with the first year of data for now, and plot the seasonal decompose and see again. Let's go just with the first year of data to magnify our magnify and see how it goes for 1 year. And the seasonal decompose is again the multiplicator model to get the seasonality. So here we can see that, guys, there is a repetitive pattern, and obviously this shows that we have spore spikes every month. We are able to see clearly spore spikes, which basically means it's a weekly basis. And next is we have to look into if there are any noise. So for noise, in order to detect if there are any noise, so the first thing that you need to know is people call this noise to be most likely a white noise. A white noise is present is because if a measurement is independent and identically distributed with mean of zeros. So white noise you can check by plotting a series of histogram, which does it look like a Gaussian distribution, and let's see, we can also plot a correlation plot, a standard deviation distribution. Is it a Gaussian distribution again? And also see how the mean and level changes over time. So I plotted the four plots are close to each other, and you can see the original original series histogram. You can see the standard deviation plot histogram here. You can find the correlation plot, which is basically the autocorrelation plot, and the mean over time. So we can see that a series does not follow a Gaussian distribution, guys. Neither the standard deviation does, because the mean is not zero. It's more. We also have a small correlation with closer measurements in time, and this could also show that we have a bit of a low seasonality. And if you see mean over time plot, you can see that some of them have high peaks, some of them this says that although our series do have white noise, but it's very small in or maybe negligible, so we are kind of ignoring it for now, guys. Is the identifying if your data series data points collected are stationary or non-stationary. So it's an important characteristic of time series, guys. A time series is stationary if the constant mean and variance over time. Most models work only with stationary, so that's why we are trying to find if our time series if our data set is basically a stationary or non-stationary. For example, if you see stock prices are not stationary, since we might see sometime a growing trend, sometime a change in the trend again. So in order to find or in order to check stationary, we use autocorrelation and partial autocorrelation plots to see how correlated are the values in terms of time. Let's look into the autocorrelation plot. For a stationary series, autocorrelation plot will quickly decrease, guys. So which we can make sure that if it's quickly decreasing, it means that your time series is stationary series. So you can see here it has definitely quickly reduced, and this is the first one is the autocorrelation, and second one is the partial correlation. And since it quickly reduced, we can see our time series is not correlated with the points. So this shows that our series is definitely a station. There are several other methods, guys. This is not the only method we can use. There are other methods like we can use rolling means, and also again plot the standard deviation of the if there is a station, if our series is stationary or non-stationary. And other famously used or commonly used test is the augmented Dirichlet test. So this test is a statistical test that used to identify if your data set is stationary or non-stationary. So basically the ideology is that the null hypothesis series that can be represented by unit root, which is nothing but it's not stationary. So that's the null hypothesis, and we have the alternate hypothesis, which is the time series is stationary. So you need to reject the null hypothesis. So if failed to be rejected, your time series is definitely going to be a non-stationary or dependent on time. So for any hypothetical test, we have p-value, which is if it is greater than 0.05, you need to fail the you need to think that it's null hypothesis and the data is non-stationary, and if your p-value is less than 0.05, the data is stationary. That means you reject your null hypothesis. So below is the example, guys, for the Dirichlet test. So below comes the Dirichlet function and calling upon the pollution today values. And if you can print all the value statistics, like we have the ADF statistic, we have the p-value, the critical values. So with respect to p-value, here you can see it is 0. So which basically says that your data is stationary. And below function, you can quickly perform. I have written a complete function where it provides the charts for the Dickey-Fuller plot, and at the same time have all the autocorrelation plot and the partial correlation plot along with the rolling mean and standard deviation, guys. So this is another method that's been used to check whether it's stationary or non-stationary, which I mentioned earlier. So once you are done with that, so since our data set is basically stationary, you don't get to see what can be done next. What makes our series non-stationary? These are the two things that basically makes a series non-stationary, which is the trend, which means the mean is not constant and it increases over time. So basically a trend, it can increase or decrease, right? So that's the first point. You need to see why that's the point which basically affect your data to make it non-stationary. And second is the seasonality. Sometimes your data may repeat over time, as I already mentioned one case where in Christmas, every Christmas there are some discounts and the sales can be high, right, during those sales time. So that's basically called the seasonality. And and uh, in order to remove seasonality components, there are methods like difference transform and log scale transform. I have just written the formula here, guys, just to provide you what these transforms are, but this tutorial does not consist of how you can remove these and see or how you can go forward with remove. We do not, since we do not have seasonality in our data set. So let's get started with the methods for time series forecasting. So in between method for time series forecasting, we need to prepare our data set, guys. So we are splitting the data set into training and test. So we have split data is basically from 2010 to 2014 and 2014 on. So we can see we have around 1461 days for training data and 364 days for test data. And for the purpose of this project, I have been using mean. I've been marking mean. I have set up a result dictionary where it will be used to uh, save all the results, guys. So name means to have the name means, so first and foremost I have developed a mean of the pollution today to identify, to also check, like try to see if the mean is better than our other forecasting model values. So mean we have collected as name mean, and also we have evaluated with the yesterday's value. So yesterday's value we already have a value called yesterday pollution yesterday. So I'm calling upon evaluate function on the today value and yes, and storing the result in the name of yesterday's value, and at the same time the predictions as well. So this is how I'm storing the data, guys. I'm storing all the results, which is the metrics where you get out of the evaluation function, and predictions are the predictions that we get out of predicting the model, future forecast. So the first and foremost time series model that we are looking into is the simple exponential. So in this model, this is basically a univariate testing, guys. You basically assume that you don't have trend in your data, no seasonal pattern. Then this is the first and foremost method that can be used to model your next time step. Like I said, you can find that in this data set I have already provided the code. The code basically is straightforward. We are calling up the index, which is the length of the training data set. We have y hat, which we are collecting in terms of list, and this is where we are calling TQDM, guys. So if this model is used to for each time series and we are calling up this simple exponential model, and then fitting on this model and predicting, and then we are collecting the y hat. So y hat is values is nothing but your predicted values. Your predicted values are nothing but basically you collect to identify what are the result evaluated metrics or the errors, and the second is the we are collecting using y hat values for prediction. The next model that we use is the Holt Winter used. Now, this is famously known as the triple exponential model. Code is similar, guys, nothing different, only that we are using, instead of simple exponential, we are only using the exponential smoothing model. So the same, we are maintaining the same steps and collecting the result dict and the prediction dictionaries. The next and important or most commonly used is the autoregressive moving average model. So here these models are basically joined, and autoregression is basically termed to be P, guys, and the number of moving average terms is termed as Q. So P is nothing but a parameter associated with autoregressive aspect which incorporate the past value. So yeah, example, you can see I've also mentioned if P is 5, your predictors for x of t will be -1, -2 till -5. The moving average, number of moving average, which is termed to be Q, is the size of the moving average part. For the code is similar here. We are not changing anything except the model is changing, where model is nothing but ARMA model. Yeah, ARMA model, guys, and we are storing all the data set, all the data result evaluation results into results dict, and the prediction value into prediction dict. Now we can now try to plot, guys, and see how a prediction original values with respect to ARIMA, ARMA prediction values. You can see we do have the ARMA model is definitely kind of similar to the original. However, if you see at this point where I'm pointing, although it is kind of mimicking the peaks, the peak is not accurate. So let's go further with another model, which is called the aggressive integrated moving average. So this is except that there is an additional parameter, which is the number of differences represented as D. So D is nothing but a parameter associated with the integrated part of model, and how it in terms of how it affects the amount of differencing to apply in the time series. So P and Q remains the same. There is nothing much different from the previous model. So another very important point that you need to consider is that ARIMA model does not support. So that is an which is basic seasonal data, which is nothing but a repetitive cycle. So for that we do have another model that takes into consideration of seasonal and also that takes into consider seasonal component. Here you can see we have that we are now using ARIMA model here represented, and the orders are mentioned, guys. I forgot to mention the earlier part is that we have to mention your order. So here we have DQ as 100, and earlier we have the values to for the P and Q as 1 and 1, which is like one lag, and one Q represents one lag, and P represents one past values. So for the ARIMA model, you can see we have again similar to the earlier code. We are collecting the differences of the test and the train to differences of the predicted values with the original value to ARIMA the result dictionary, and the prediction values to the prediction dict values. And when we plot, you can see a similar one, similar to ARMA model. I don't find any much difference. So let's go forward with another model, which is called the seasonal octo regressive integrated moving average, SARIMA. So seasonal is an extension of ARIMA model, guys, except that we can include the data with the seasonal. So So for the trend element, we have the similar trend element already as per the provided is PQD, which is trend auto regression order, trend difference order, and trend moving average order. Now for the seasonal, we do have PQD, but it is represented in capital letters. So that's how you differentiate the seasonal elements and the trend elements. And the P represents seasonal autoregressive order, D represents seasonal difference order, Q represents seasonal moving average order, and M, which is nothing but the number of steps for a seasonal time period, because it's a cyclical, right? It either every year there is a cycle, right? Like for example, Christmas, every year you have Christmas. So that you have to represent. So the model remains the same. You are using SARIMAX algorithm, and you represent the order 100 and seasonal order 003. After providing the order and seasonal order, we can go forward with fitting the model and collect the results like result dictionary and prediction dictionary, guys. So, and later on plot, if you look into plotting the original versus the model, you can see now we are kind of reaching to the original value. So the point earlier that I mentioned, it was below for ARIMA model and ARMA model, while for this model it is kind of reaching to the original. So this seems to be better, guys. So let's now look into the evaluation. For the evaluation, the metrics used are basically MAE, which is mean absolute error, and RMSE, which is root mean squared error, MAPE, which is mean absolute percentage error, and R2, which is nothing but the coefficient determination. So MAE is nothing but it's a very good KPI for forecast accuracy, guys. It means the absolute error. But however, one issue is that it is not scaled to the average. And RMSE is the root mean squared error, and it's the square root of the average squared error. So it's square root of MSE. And MAPE is similar to mean absolute error, except that it is in percentage, which is basically helps us to interpret the results. And R2 is nothing but the coefficient determination that represent how well the model fits the dependent values. So since we already have the results in a result dict, I have printed out the results for you here. You can see for all the models that we have along with the yesterday's value and name mean, we do have so these are the below my thoughts, guys. So below my thoughts are nothing but here we can be honest, RMSE emphasize only the most significant error, while MAE gives the same importance to each error. So that is the main caveat here when you always consider RMSE and MAE. Now in a model, you have to see that MAPE was basically best in ARIMA, SARIMA. So I do have a spelling mistake. Let me change that. Some of the spelling mistakes. Apologies for that. So so we can see MAP is greater in was the best in SARIMA model with 91%. So the lowest is considered to be the best. So 91% is the best here for MAPE. And in terms of RMSE, the best is coming from ARMA model. ARMA model, which where we are considered is to be the lowest. So 64.86 is best for ARMA model and similar to R2. So 0.37 is the best, similar for MAE guys. MAE we find that 47.10, which is the lowest in terms of MAE for ARMA. So in terms of our analysis today, if you look into seasonal component, we would definitely go in fix with SARIMA Max, because MAP is really good here in this model. And like I said, since RMSE and R2 is rather only specify errors when there are specific or a significant error happening in the model, it will only show an error. So I would definitely, in terms of this analysis, I would go for the SARIMA model for this objective, guys. That is all with the analysis. So that is all guys with the portfolio. I will be linking all the codes and datasets used in this project and in the description box. Please do visit if you would like to download the code and try to play around with the dataset and see how you can improve the model better. So this is the whole idea of the second portfolio ideas, guys, and I hope this video was useful. Please do like, share and subscribe if you feel this video was useful. Have a great day ahead. Bye.